Dear viewers, I'd like to talk to you about the measurement of light, and in particular the unit candela. I think that there are several deficiencies from which this unit suffers, and for each I've also, I believe to have found suitable corrections. Well, let us go through them one by one, and perhaps this video will have some effect. Hopefully it will. First of all, let us talk about this. LMS stands for large, medium and small, and these are basically used as designations for the cones within our eye. As you know, there are three different types of cones, and each has a different sensitivity function. So let us recall that the lumen, which I'm going to use here instead of the candela, because I'm also trying to make the argument that it is a more fundamental unit, the lumen, than the candela. Basically, in order to determine the lumen, the total luminosity of an object, what we do is we take a sensitivity function, which is here denoted by lambda, and integrate it against the power, the energy per second transmitted via light waves of a certain wavelength. One may also use frequency, whatever your preference is. But in fact, our eye has three different kinds of cones, and therefore it would probably be better to also have three sensitivity functions, because in this way it is possible to measure the effect on each type of cone individually. Also in this way we only obtain a way of making sense of the Grassmann additivity law, which states that this lambda is supposed to be the sum of said sensitivity functions. So the thing is, there exists experimental values for each of these, and also for this one, but they are not necessarily consistent in terms of this law, with possibly a weighting, which I'm going to explain later. So that is the first issue I have with this definition. There is a more mathematical issue, because we've seen, so suppose we've solved the first problem, and now we are considering integrals like this in order to define our lumen. the problem with this is that we can't really evaluate this integral precisely. So we need some sort of numerical integration method. And I would suggest to enforce a standard integration method. The reason behind this is that we want people not to be able to choose their own numerical integration method, because they may use it in a fraudulent way. For instance, if they use an integration method which makes the light bulb that they produced look particularly bright, even though it really isn't. So that is another suggestion that I have. So perhaps call that numerics. Then there is an additional sort of mathematical problem, which is, let's say we have defined lambda, which we can only define via discrete values, because we don't. So an arbitrary continuous function would require infinitely many, countably infinitely many data points at the very least. And so we don't have this capacity, obviously, in our computers. So what we need to do is define it at particular values. Well, I mean, I've got no problem a priori with a regular one-dimensional grid. But the thing is, if we've got all power concentrated at a particular value, so let's write this way. Maybe multiplied by a constant, where this is a Dirac functional. And we don't really get anything out of numerical integration methods that have been designed for continuous value distributions. So what I suggest here, what one should do, so here let's call this omega naught, where it's concentrated. What one should do is, let's say these two values have been determined experimentally, or are somehow in the definition of this lambda. So let's say W naught or omega naught or whatever you want to call it is here, and then we've got a distance here. Let's define that to be mu d naught, where d naught is the distance between two grid points, and then we have here 1 minus mu d naught. And what one could do is simply approximate this integral by c times mu, and now we take the value at let's call that omega 1, omega 1, and this omega 2. So this is where we can evaluate this, 1. This is where these two values are where we can evaluate lambda. Okay. So this is number 3. Let's move on to number 4. I would call this scopic vision. It's probably a silly name, but our eye does not only have cones, 3 different types of cones, but also rods, one kind of rod, and that's activated under dark circumstances and in dark environments, and that they behave differently and have a different sensitivity function than the cones, and moreover, under certain conditions they also determine the brightness together with the cones. That's called mesoscopic vision, and it's sort of half dark environments. We see here that we have a dependence on environmental factors, even of a unidirectional vision. So what we need to do here is first of all determine these environmental factors, but since it does depend on environmental factors, it makes no sense to give a value for all environments. Also, we'll later see that all these psychological factors that influence how light is perceived are really different among human beings. So what we need to do is treat these differences as some sort of statistical noise and give confidence intervals instead of a fixed value. So it's sort of admitting, not only admitting that we don't really know the precise value, but also quantifying how much insecurity there is. So then there is a big problem. There's actually a massive paywall in front of the specific sensitivity function that is used for the definition of the candela. That is really bad, because you need to pay 150 euros in order just to know how bright your light bulb is. For instance, I myself, being a mathematician, don't have that kind of money. So The solution is quite simple, no paywall. And I'll go into more details in a few moments. Then, how is this function that you are supposed to pay 150 euros for determined? It's determined by bad experiments. Why are they bad? Because they are based on subjective experience. So what happens here is we have light, and it travels into the eye, and then into the brain. And inside the brain there is some sort of perception of the brightness. This is what is being measured in these experiments. They ask people, how bright do you perceive this to be? But there's a problem about that, because the brains are so individual that basically this measurement is very imprecise. So if you try to make a Monte Carlo approximation of pi, you realize that it's going to take very many points that are randomly generated in order to. So I'm talking about measuring pi by measuring how many random points fall into a certain circle. By generating random points in a square and then determining the ratio of the points that are inside a circle. So here's the diameter. But this doesn't work very well, because you need a massive amount of points in order to get a halfway reasonable value. And this, what happens in the brain here, is sort of like noise. So the suggestion is to instead use something that we have a chance of measuring, which is the sensitivity of the individual cones. So this is something we might even grow in a lab on someday, but this moves it into the domain of physics. There has been a study once in a psychology journal which stated that 60% of studies in psychology journals are not reproducible. So, I mean, I don't know if it's reproducible or not, but it's a worrying indicator. Let's move on. So I've already given this nice integral, which defines the lumen, or which at present they define the lumen using the candela, but I really prefer it if it was the other way around, because then it would be consistent with watts and sort of watts per steradian, which is used in order to determine radiation in a certain spatial angle. So this quantity is usually given as dimensionless. Let me put the 3 question marks here, because I'm really of the opinion that it would be much better to assign to it the unit of lumen per watch. Remember, we are at a specific, so this is a lowercase w or omega, and this is a capital letter, uppercase, and so the point is that given this fixed frequency or wavelength, whatever your favorite convention in this regard is, given that this unit is sort of the one that's logical, because it gives you in the end how many lumens we assign to this, which is something like this, watts per nanometers, if you take the wavelength definition. So that was number 7. Let's call that dimension. Let's move on to the next one. What do we do about colorblind people? These have a different sensitivity curve, and so the problem is that they have a different composition of cones, and therefore the brightness they perceive is different. So what I would suggest is what I've already suggested, to split it up into to split up the sensitivity function into, well, let's call that L, M, and S, into 3 components for each cone, and then add some coefficients here, which are according to the composition of the interior of the human eye, according to the proportions with which the cones occur. So no, that can't have been so by the way, I'm a number theorist. This is number 8. Sorry about that. But mistakes do happen, and it's important to acknowledge when they do happen in order to make some progress. So then I've told you that it costs $150 to get access to the defining values of the candela, to the sensitivity function. Another problem is these get updated. So let's call that updates. A better way would be to have a publicly available website. What do I mean by that? A website from which you can download everything for free, and which is maintained by a team of dedicated scientists who are really after finding the best values in some sense, according to a certain precise definition, as indicated before, in certain standard conditions, with error margins and so forth. Finally, let me end by mentioning astronomy. So astronomers have the need of measuring light in a sort of scientifically well-founded way. So they usually just measure the intensity at a certain frequency, but I'm under the impression that they discriminate against blue supergiants. Because that's where a type of cone is really very sensitive, which is not really taken into account by their standard frequency. And I hope that the suggestions I've made will perhaps pave the way for the lumen also being used in astronomy, so that we get rid of the discrimination against blue supergiants. Well, actually, now that we are talking about it, let's perhaps also talk about radiation. And there are two units of radiation where there is a bit of a problem. The first is the becquerel. So the unit of this is second to the -1. It's the same unit as the hertz, which is also second to the -1. So these are in a way identical, but if we compare that to the mole, we have the chemical unit of the mole, which is approximately 6.022, I think. This number, I'm not quite 100% sure. This number of particles, chemical particles, so we could sort of identify this as an underlying unit. And here, in contrast, we have events. But we don't have an extra, we don't have an extra unit that indicates events. It's just per second. So that's a sort of an inconsistency. So let's draw sort of a inconsistency lightning here. But what's really important is what I've got to say about the sievert, because the sievert makes the mistaken assumption that radiation has an equal effect on each part of the body. So for instance, if we have like a sort of guy and there's like radiation to the brain. Oh, hang on, maybe we ought to change the hair a bit. Oh, let's just leave out the hair. Let's take the sort of person without severe neural deficiencies, and there's radiation. Well, it would affect the brain in a different way than other organs, which are perhaps not so essential or have perhaps more or less resilience to radiation. So my proposal for actually measuring a hypothetical unit which would supersede the sievert would be to have some sort of body suit with many different sensors adjusted to the organs, which would have to be tailored to a person according to some sort of specifications. So thank you for your attention, and I hope some of you can do something with this and perhaps implement some of it.